All right, let's dive right into this explainer. If you've ever stared at a wall of complex algebra and felt, well, totally overwhelmed by those little floating exponents and those strange log symbols, you are exactly where you need to be. Today, we're taking the seemingly intimidating world of exponential and logarithmic laws, and we're going to transform the whole shebang into a clear, intuitive translation game. It's like building your own mathematical toolkit.
But before we map out our journey, I want you to keep this single core mystery in the back of your mind. Whenever you see a logarithm, the only thing it's really asking you is this: to what power must the base be raised? Seriously, that's it. It's not some magical spell. It's just a simple question of finding a missing identity.
So we're embarking on a bit of a mathematical boss battle today. Here's the game plan. We're kicking things off with the sheer power of exponents. Then we'll unlock the logarithm decoder ring, equip ourselves with the laws of logarithms, solve an impossible equation, and finally we'll defeat some real-world problems while dodging a few really common traps. Okay, let's jump straight into Section 1, the power of exponents, unlocking rapid growth and decay. We're going to see just how fast things can truly escalate. Take a look at this. This brilliantly illustrates exponential growth. You can see the value literally doubling at every single step. When our starting value is at 0, we're at 3. But watch what happens when that x value increases by just one single unit. 3 leaps to 6, then 12, then 24. This isn't just a steady, predictable climb, right? It's explosive momentum. That base number of 2 is acting as a massive growth factor.
And when we compare how a population booms versus how, say, a machine loses value over time, it reveals the two main flavors of our exponential formulas. On the one side, we have exponential growth. That's where your base is greater than 1, simply because you're adding a rate, r. But on the flip side, we have exponential decay, where the base is less than 1 because you're subtracting that rate. It's the exact same fundamental math, just pulling reality in completely opposite directions.
But here's where we run into trouble. It's super easy to figure out 2 to the power of x equals 16, right? We know 2 times 2 times 2 times 2 is 16, so x is just 4. Easy. But what about 3 to the power of x equals 20? Well, 3 squared is 9, 3 cubed is 27, so the answer is floating somewhere in between. And right here, we had a mathematical brick wall where the exponent itself becomes this unsolvable mystery using just standard algebra. To smash through that wall, we move to Section 2, the logarithm decoder ring. This is your ultimate translation tool. The absolute crucial point here is a surprisingly simple translation rule. It proves that exponents and logarithms are honestly just two sides of the exact same coin. Take the exponential form. 2 to the power of 3 equals 8. Now, flip the coin to its logarithmic form, and it becomes log base 2 of 8 equals 3. They're communicating the exact same universal truth. The logarithm basically reaches up, grabs that floating exponent of 3, and yanks it down to the ground level so we can actually work with it. Real game changer. Now, just like learning a new language, you do need to know the specific dialect. In our case, those are the common base 10 and Euler's natural number. If you see log x with absolutely no number attached at the bottom, it's just a common logarithm, which assumes a base of 10. But if you spot ln x, that's the natural logarithm. It relies on Euler's number, which is approximately 2.71828, and that is literally the fundamental constant of continuous growth in the universe. All right, moving on to Section 3, the laws of logarithms. It's time to equip your mathematical toolkit and see how we can manipulate these formulas however we want. Our very first tool is Law 1, the product rule. It shows us how complex multiplication elegantly translates into simple addition. Imagine breaking a heavy anvil apart. If you have the log of two numbers being multiplied inside, like 8 times 4, you can break them apart and just add their individual logs. So log base 2 of 8 is 3, log base 2 of 4 is 2. Add them up and you get 5. It takes heavy mathematical lifting and makes it incredibly light. Let's keep the rhythm going with Law 2, the quotient rule. Think of solid blocks splitting apart, where division beautifully reduces down to basic subtraction. If you have a fraction inside your logarithm, you just take the log of the numerator and subtract the log of the denominator. So, log base 2 of 32 minus log base 2 of 4 simply becomes 5 minus 2. And the result? Just 3. It's such a remarkably clean process, isn't it?
And finally, our ultimate weapon is Law 3, the power rule. This allows us to yank that frustrating exponent right down to the front. For example, if you have a power of 4 stuck inside a log base 3 of 9, it absolutely doesn't have to stay stuck up there. We just slide it right down to the outside as a multiplier. Since the log base 3 of 9 is 2, the math simply becomes 4 times 2, which gives us 8. Boom!
Okay, with our toolkit fully equipped, it's time for Section 4, Solving the Impossible, Defeating the Mathematical Boss.
Notice how our new translation toolkit easily breaks down that complex algebra problem from earlier into 3 really digestible bites. Remember 3 to the power of x equals 20? Well, in step 1, we apply our decoder ring by taking the log of both sides. In step 2, we use our ultimate weapon, the power rule, to pull that mysterious x right down to the front. Now x is just multiplying. And for step 3, we simply divide both sides by log 3. Punch that into your calculator and you find that x is approximately 2.73. See that? You just solved the impossible.
Which brings us to Section 5, Real-World Applications, High-Stakes Scenarios. Let's look at a few examples and see how these formulas actually govern everything from biology to your bank account. Imagine trying to calculate the growth of a population over 5 years using the exponential formula. Let's say we start with a community of 500 people, and they're growing at a steady 8% annually. By plugging this into our exponential growth model, we set our initial amount, add our rate to 1 to get a 1.08 growth factor, and then raise the whole thing to the power of our 5 years. And the math reveals exactly 735 people. This really shows the tangible result of exponential momentum. It's not just a rough guess. It is a highly precise mathematical model of exactly how biological systems scale up over time.
But even more crucial to us is your wealth, where continuous growth utilizes Euler's number. This is the absolute magic of continuous compound interest. Imagine investing 10,000 rupees at a 5% interest rate that compounds without stopping for 6 straight years. Because the compounding is continuous, we bring in E, Euler's number, raising it to the rate times the time.
And this reveals the literal value of the math, turning a base investment into an impressive sum of 13,499 rupees. Understanding exponents and Euler's number isn't just some boring academic exercise, it is literally the mathematical engine that drives global finance and personal wealth.
Okay, before we wrap up, let's look at Section 6, the traps. We definitely need a helpful warning about the common mistakes and red flags that catch even the smartest students. You are going to want to rapidly lock these red flags into your memory. First up, you can never, ever apply logarithm laws to simple sums and differences. Log of a plus b does not equal log a plus log b. Seriously, don't fall for it. Second, never forget that your logarithm bases have incredibly strict rules. They must always be positive, and they cannot equal 1. And finally, please keep your dialects straight. Do not mix up the natural log, ln x, with the common log, log x.
I'll leave you with this final, powerful question. Whenever you see a variable trapped in an exponent, ask yourself this on every single test. Can I rewrite both sides with the same base? If the answer is yes, great, you're good to go. But if the answer is no, well, you now know exactly what to do. You grab your logarithm decoder ring, you take the log of both sides, and you use the power rule to yank that exponent back down to earth. So, the next time you face a wall of algebra, ask yourself, are you going to let the numbers dictate the terms, or are you ready to be the translator?